Every fiber optic link faces one invisible challenge: signal loss. From the first pulse of light at the ult to its arrival at the ONT, energy gradually fades. Managing that loss is the essence of optical power budgeting. From the ult in the central office, laser pulses enter the fiber, traveling through connectors and splitters until they reach the ONT in each subscriber's home. Each connection, splice, and meter of fiber adds a small but measurable loss, usually expressed in decibels dB. Understanding these losses is the foundation of every optical power budget. In every fiber optic link, each component slightly reduces the light power. This total loss, measured in dBm, defines the allowable power budget. Using an optical power meter, engineers observe real values like 18 dBm or 27 dBm, depending on distance and split ratio. If received power falls below the ONT sensitivity, the link fails. The power budget marks the boundary between a successful and an ineffective design. The OLT is the source of power. Typical GPON transmitters generate around +4 dBm optical power at 1,490 nanometers. This becomes the starting point of all calculations. The ONT at the subscriber end can detect as low as -27 dBm. The difference between output and sensitivity sets the total available budget, roughly 31 decibels, for GPON. Loss happens because light encounters imperfections, microscopic scattering, absorption in the glass, and small mismatches at splices and connectors. These tiny effects accumulate along the fiber, reducing total optical power. At 1,310 nanometers, single-mode fiber averages 0.35 decibels per kilometer. At 1,550 nanometers, it drops to 0.25 decibels per kilometer. These small differences become crucial over long runs. Each connector contributes around 0.3 decibel loss. Splices add about 0.1 to 0.2 decibel. 2 connectors and 10 splices can easily exceed a full decibel in total. Splitters divide optical power among many users, but division means attenuation. Energy shared is energy reduced. That's where split ratio becomes vital. A 1/16 splitter loses about 13 decibels, 132 around 15 decibels, and 1/60 for nearly 18 decibels. Each step expands coverage, but shrinks available power. Example, 10 kilometers fiber adds to 0.5 decibels loss, connectors 0.6, splices 1, and splitter 15 decibels, total around 19 decibels. With a 31 decibels budget, the link runs perfectly. Any extra loss still keeps margin for safety. Doubling the split doubles endpoints but raises loss to nearly 22 decibels. Still functional, but system margin becomes tight. Every connector now counts. Technicians use Optical Power Meter (OTDR) and VFL to verify actual signal levels. These instruments reveal if design math matches the real-world fiber path. During installation, every connection is inspected. If measured loss exceeds design limits, fibers are respliced or connectors cleaned until power restores. International Standards ITU-TG 984G 987 FOA TIA AI85 recommended ranges. Following them ensures interoperability and long-term stability. When split ratio or distance exceed the budget, amplification or redesign is required. Future steps involve EDFA and SOA amplifiers to extend reach beyond passive limits. Urban FTTH networks often balance 130 to splits with 10 to 15 kilometers reach. Rural networks prefer 1/16 split to ensure strong margins across longer routes. It's always a trade-off between coverage and reliability. The optical power budget defines performance borders and makes split ratio decisions possible. It tells engineers how far light can travel and when amplification becomes necessary.